This Raw Green episode is brought to you by OBI, a sustainability consultancy firm specialized in life cycle assessment and decarbonization strategies. For more information, check oneobi.com or visit our page on social media. Links in the description. I am Francesco De Lieto. I am passionate about sustainability and green technologies. Welcome to a new episode of Raw Green. As many of you know, increasing the share of renewable energy in our electricity grid it is crucial for combating climate change and reducing our reliance on fossil fuels. And wind power plays a key role in this transition. But here's an interesting fact. While onshore wind farms are more common, the real untapped potential lies offshore. It is estimated that a whopping 80% of the world's offshore wind resources are located in waters deeper than 60 meters, where traditional fixed bottom turbines aren't practical. This is where floating offshore wind farms come into play. These innovative structures can be deployed in deeper waters, capturing stronger and more consistent winds. Developing and deploying offshore wind projects it is no easy task. It involves a complex process including area analysis, obtaining permits, securing financing, installation, operation, and eventual disassembly. It is a monumental effort. Challenging as well is quantifying the various environmental impacts a project of this scale can have throughout its lifetime. To help us gain some insights into the scale and impacts of floating offshore wind projects, we have our guest of today. She is a talented researcher from the Politecnico di Milano in Italy, and she has published a paper on this very topic, a life cycle assessment of a massive floating wind farm in the south of Italy, currently in the permitting stage. Please welcome Gaia Brussa.
Hi, Francesco. Thanks for having me at Row Green.
Ciao, Gaia. Welcome. Why don't we start by you giving us an intro about yourself, your area of research and expertise?
Of course. So I'm Gaia Brussa and I'm an environmental engineer. I graduated at the Politecnico di Milano, where I started my research on the topic of life cycle assessment of wind energy, in particular on wind energy on floating platforms. And currently, I'm working with a group that is called AWARE, which stands for Assessment on Waste and Resources, as we apply the methodologies of life cycle thinking. So, for example, life cycle assessment for the environmental impacts to environmental technologies in general. But actually, the first scope of the research of the group, led by Professor Grosso and Professor Rigamonti, was waste management. So it's a quite a new topic for us as a group to apply the LCA to wind energy or renewable energies in general. That started actually with my master thesis, from which the peer review article that you mentioned actually was born. And yeah, so we now have different topics on and research activities on the topic of wind energy, not only offshore wind energy on floating platforms, but also other innovative kind of wind energy generation technologies. Or, for example, we also apply the same kind of method to quantify the potential impacts of other renewable energies. And also, with another research project, we also try to focus on the end of life of this kind of technologies that will actually be of a great importance for the energy transition, but at some point they will become waste. So we are like connecting the points of the expertise of my professors and this kind of new topic.
Those are all very interesting, and we'll go back to the end of life on wind projects because it is a
Okay.
very interesting and complicated topic too. But let's start by talking about your research, the research that you published not long ago, which is a life cycle assessment of a floating offshore wind farm that it is right now in one of the various permitting stages. This wind farm, it is about 50, 60 kilometers south of Sicily. Can you please give us an overview of what this paper is about and what is included? And then afterwards, we'll dig into the research, into the results and the details.
Okay, of course. Yeah, as you said in the introduction, actually, the interest for this research was because this kind of floating wind farm would be very massive, so a huge deployment off the coast of Sicily, with an installed power of like 3 gigawatts and almost 200 wind turbines of the rated power of 15 megawatts, so quite large wind turbines that we realized were not covered in the literature as a life cycle assessment. So there was this intuition by my professors to say, okay, this is a huge deployment that can generate a lot of green energy, because actually wind energies are renewable energies. You don't have direct emission of greenhouse gases and of pollutants, of course, during the generation of energy, on the contrary of like fossil fuels, as we know. But of course, we need a lot of things, like a lot of materials and a lot of energy, and to transport them in the location of the installation. So we need a lot of things that we need to quantify, and that can have, of course, other potential environmental impacts. So the rationale behind the life cycle assessment is to understand all over the life cycle of a product or a service. So in this case, the generation of wind and electricity by wind power, which can be the environmental impacts that we have all along the supply chain, but also the like future phases that the system that we are analyzing could have. So in principle, we try to have whole and holistic approach, and to cover what is called from cradle to grave, so from the raw material acquisition to the end of life, all the phases of a wind farm. So as I said, the extraction of materials to the manufacturing of components, then the transportation, the installation, the operation and maintenance phase, where we have also spare parts and so on that we have to supply again during the 20, 25 years that are also 30 years that a wind farm can be operating. And then we will have also the dismantling and the treatment of the waste that we will produce at the end. So our idea was to try and cover all the phases, and also to focus not only on the wind turbine itself, so just the structure like tower, nacelle, and blades, and also the floating platforms that we also understood that it's a quite important and peculiar thing of this kind of farm, which is of course farther from shore. So, for example, this is avoiding some impacts, for example, land occupation or visual impacts that can be also important for social acceptance of this kind of technologies. But of course, this requires another technology, for example, to keep this huge wind turbine floating over there with harsh environmental conditions and so on. So we wanted to understand how much does it cost, so to say, to the environment. And another important thing to take into account is also um, the um, the delivery of the energy to the shore, because of course farther from shore it's better, because we either don't see the deployment, or is very little, so it doesn't disturb us in that sense. But of course then we have to transmit the electricity produced, for example, for longer and deeper seas till the land where we can use the electricity produced. So in this case, it was also a very important thing that we tried to include in the system boundaries, so to say. And although it was very difficult because, as you said, the project is still under the permitting phase, so it was not the final project, so it was preliminary, and we also didn't have any kind of contact with the company that was developing it, but we wanted to be totally independent, and we just relied on data that was publicly available on this
Publicly available.
website of the environmental ministry. So on top of that, we tried to recover data from the literature, and so to build the model of
Yeah.
the project.
Wonderful. Well, it is very comprehensive. If I have to say, to cover all the phases from the acquisition of the raw materials till the end of life treatment. It is no easy task, especially if you don't have access to primary data, which is also a very important topic. Let me ask you. So let's talk about for a second about the results. Okay, and what I wanted to ask you it is wind turbines, floating platforms, and cables plus transformers. Let's say those are the three main categories of components. Which one is the most impactful and why?
Okay, actually, it depends. Because I have to say, as a first thing, that we decided to cover 8 impact categories. So we just didn't want to focus only on carbon footprint, that is very well known, and very popular at the moment. So we didn't want just to see what is the impact and potential impact on climate change, but also evaluate other impact categories, so other impacts on other environmental issues, for example, acidification, eutrophisation, the photochemical ozone formation, and also the depletion of not renewable materials in the sense of minerals or fossil fuels. And of course, every kind of environmental issues is connected to different emissions or consumptions from the nature. And so, for example, this can lead to results that are not only in one direction. But if we would like to focus at first on climate change, since renewable energies as the first mission of reducing greenhouse gases, what we can say is that the hotspot, so the most impacting component in this case,
Yeah.
is the floating platforms. Yeah. This is due to the fact that it's like a huge quantity of steel, and of course, steel in its production is emitting greenhouse gases. This was actually uh, quite the same for all the other or the other impact categories, in which either the wind turbine structure or the floating platform was the most impacting thing, except the the called depletion of minerals and elements, in which we saw the importance in a negative way of submarine cables. So the transmission of electricity, due to the fact that we modeled it as it was as it was considered at the time, almost 500 kilometers of submarine cables to connect the plant to Campania region. So instead of Sicily, because of the some like restrictions on the net of the island. And of course, this was a very huge amount
Tremendous.
of copper
Yeah.
and other elements, because of course the submarine cables are more complex in the structure, and this was like almost half of the impacts of all the life cycle was given by the submarine cables. So this was also something that we didn't expect, because of course copper is also something that we expect is restricted, but in any kind of technologies related to energy, then we will have some kind of transmission system. So it will
Yeah.
be also difficult to avoid its usage.
Okay. So why the floating structure it is the most impactful one on the climate change?
No, the fact is that actually the semi-submersible platform that we chose to model, since we found the data in the literature for its dimensioning and its design for the 15 megawatts wind turbine, is in principle 4,000 tons of steel, and this weight is just for one turbine. So
Just that. Mm.
putting together almost 200 wind turbines and this kind of steel requirements, this was actually what was giving us these results. And of course we didn't have the chance to try and test other type of designs, as we know that it's the semi-submersible platform is not the only one floating platform that we can employ, but of course it was difficult to retrieve data on the design. But of course, something either in the direction of reducing the amount of steel needed for this kind of design. So, for example, other types of design, or we know that some kind of research is doing in this kind of direction, or for example, trying and having other types of material. So someone is also experimenting with concrete, or like mixing concrete and steel structures to try and avoid all these huge amounts of steel. Or we should like hope that there are some kind of implementations in the steel industry to reduce their carbon and greenhouse gases emissions,
Yeah,
and
more
in the
sustainable steel. So, moving on the various stages of the life of a floating wind farm project. Let's talk for a second about O&M operations. Uh, what are the impacts that you were able to analyze and highlight in your research?
okay. So for operation and maintenance, I have to say what we actually tried to model, because, of course, as the project was at preliminary stage, we didn't have actually the actual maintenance plan that they were planning to have. So we tried to find in the literature some kind of information about the spare parts that were needed for like having 30 years of operation of a wind farm. So in principle, it was a representation quite simplified with respect to the reality, in which we have, of course, a lot of transportation for inspections and other kind of human labor at the wind farm itself. But of course, since we understood that the main parts of the impacts are almost always related to the acquisition of materials and the production of the components, we at least wanted to understand, as a first attempt, how many things we should have as spare parts, so we should supply during the 30 years of operation and deliver them to the installation location. So this actually was a bit difficult, as we didn't have the expertise on the maintenance of wind farms actually, and also there is some kind of papers on the topic that also were almost published in the same time I was doing my thesis. So not all the results I could actually use for my model. And what we in the end understood is that on average the maintenance phase was counting for 10%, or about so, in all the impacts categories. And it was the second most important phase after installation and dismantling. So where we tried to model the fact that we need to transport with the specialized vessels the things from the port
Hmm.
to the offshore location. And this, of course, open a big discussion, maybe because the fact that we have to simplify the reality, of course, bring us some results that we can use to have some kind of idea of how much something is actually impacting or not, but it's not actually evaluating the impacts of the reality itself. So, of course, when we try to broaden the scope, so to have all the life cycles stages, then of course we, on the other hand, maybe are losing something in the details because we don't have the technical expertise to know all the things. So we need to rely on other researchers' data and so on. So maybe this is bringing more uncertainty.
Hmm.
But from our point of view, not having any kind of results of this kind of system, it was more important to try and build all what was possible and to, in the end, have a number that is not the number representing the final result, but is just giving us an idea which can be used for making comparisons and understand what we should improve, either in the sense of the reality or in the sense of the modeling, because
Yeah,
of
yeah,
course we have to find a trade-off in this case.
T- totally.
This was
Eh,
one of the
yeah, this was one of
that this
the.
was one of the stages that we sorry.
Okay. Well, look, you mentioned before that you mentioned about assembly and dismantling operations. Okay. And which they were modeled the same. So you modeled the disassembly the same way that you modeled the assembly, if I remember
Yeah.
correctly.
Mm-hmm.
And
Mm-hmm. Yeah, exactly.
approximately 20% of the global warming potential comes from these two phases. Can you please explain in these two phases where are the hotspots? Why so high? Is it because of the transportation of the floating structures of the turbines? You have to do 50 kilometers to go and 50 kilometers to come back for every floating structure and wind turbine, and multiply by what is it, 200 turbines. Then you have the cables, the transformers, the transmission systems, and so on. But where do you find the hotspots in the assembly and disassembly?
Yeah, actually, there was two main things. So the installation were actually modeled as strips of the specialized vessels, so the emissions and the use of heavy fuel oil for them. And the assembly instead was modeled as electricity consumptions and diesel consumptions for building machines. So also these phases were actually very simplified, and we can say that the assembly is almost all related to the consumption of diesel.
Okay, and talking about the whole life cycle stages combined, if you want to look at the project from let's say the angle of an investment into environmental resources, okay, what would be, for example, the carbon rate of return or the carbon payback? When would you break even?
If I'm not wrong, it was something around a year in case of carbon payback time.
Wow.
So you have like almost 29 years where you are
Yeah,
producing, so to say, free carbon free energy.
yeah.
So it was very,
This
of
using the
course,
methane as a baseline, and but what would
exactly.
be the carbon intensity of this wind farm per kilowatt hour? How many grams of CO2 per kilowatt hour?
The result was 31
Okay.
kilograms per megawatt. So it was of course in the range that you can find in the literature because it's very it's quite wide, but it's much lower than other fossil fuel based
Oh yeah,
yeah
lots.
technologies. The fact
It is actually very close to onshore wind.
mm,
31 kilograms per megawatt hour or grams per kilowatt hour. You have methane that it is usually in the range of 5. 5 to 700 grams
Hmm.
per kilowatt hour. Then you have coal, which is 800 and even over 1,000 grams. So yeah, absolutely, it is a fantastic result. But look,
Yeah, of course.
yeah, yeah, go on.
Yeah, I just wanted to add that, of course, the result that we have is per unit of electricity generated. So, also the siting of the plant was a bit not advantageous in that sense, because the capacity factor, so the time that the plant is operating at its nominal power, was just 34% of the time. So normally they expect to have capacity factors around 50% for offshore wind farms. And that, of course, means that more energy you are producing, the more you are like discounting the emissions that you are having. So
Yeah.
we also got the review during the revision of the paper now for the submission in the peer review journal, that it was very low. But I said it's like a real number. So they had the analysis of the winds of the site, and they just got this result. So it was not voluntary to have it like a low number, but it was the real one. So in the sense, if they could have the same kind of plant in another spot where there is a bit more wind, then the result would be even better.
Even better. Yeah, nice,
That is
fantastic.
the point of this kind of model. Yeah.
Fantastic. Yeah, it is. Okay, now let's talk about end of life of wind turbines first, and then the overall project in general, which is a hot topic. I've
Hmm.
seen, and read about various ways of recycling the turbines, making benches or using as carports, or sometimes even
Hmm.
bridges, just trying to get the fiberglass, which is actually a kind of a polluting material, composite material. Now, can you please give me an overview, according to the research that you've done for this paper, on how currently turbines are disposed and or recycled?
Okay, sure. Actually, as you said, the most problematic thing in the wind turbines are wind blades, because actually they are made of composite materials. But except of that, it can be assumed that 85 to 90% of the wind turbine structure can be recycled, because it's made of
Wow, that's
principally
high.
metal. So we have aluminium, steel, a lot of steel. Then we have aluminium or copper and so on. And this is in principle already quite established. The recycling of this kind of metals is not a problem. What is actually the problem that is still need to research, and also to get this research on the industrial level, is the treatment of composite materials. So in principle, we have fiberglass reinforced plastics that are used for the blades. And the problem is that, of course, the focus in the design of this material was to have a very resistant material that can stand the loads and the harsh conditions for a lot of years. So the focus was not on the end of life and the recycling, and having this kind of characteristics for the useful life, then actually pose some problems at the end of life, because it's very difficult to separate the the fibers from the resins that take them together. And of
Yeah.
course, this is the focus of recycling. You can also have some projects on repurposing. So, as you said, using the waste in another way, so that you don't have to treat it at that time. But of course, in the future, you will have at some point to do it. So we can just postpone the problem a bit, and but then we also need now or in the near future to have solutions for what we have already put in place. At present, most of them are actually sent to waste to energy plants so that you can at
In your
least recover
research?
the energy of the organic component.
Yeah. So in your research, it was mostly diverted to waste to energy facilities.
Yeah, exactly. As we
Okay.
found that it is the most widespread solution because some countries are banning the landfilling of this kind of waste. So the other option that is not, of course, not a material recovery, so in the sense of recycling, but is just energy recovery. At least there is this option in which the organic part, so the resins, is burned and then energy is produced, or there's also the possibility to treat co-process them in cement kilns, where
Mm.
there's the burning of the organic part to have, instead of the conventional fossil fuels that are like burning for cement production, but also the fiberglass is substituting part of the raw materials as inerts, so they are used also in the production of cement.
Very nice. Well, look,
So this will be
there is.
closing the loop.
Yeah, exactly. You have a full circular economy project. That would be actually fantastic. But like you said, they have been designed to withstand some of the harshest conditions. You have the super strong winds, waves, salt particles, which they corrode everything. So, and they are
Mm,
subject to those conditions 24/7, 365 for 20, 25, 30 years. So, yes, I understand what design. I've seen
yeah.
some designs, but that's for onshore wind turbines where they start to make them in plywood, where the
Mm,
design already takes into account the end of life treatment and various scenarios of recyclability or repurposing. But anyway, very, very fascinating. And floating offshore overall, it is definitely a wonderful opportunity to decarbonize energy production. But there are also other form of wind production or other wind technologies. Have you come across some of them during your research, your literature review on other form of wind production and also their carbon intensity? It would be good to know.
mm. Yeah, actually, recently we got involved in some projects regarding airborne wind energy. So that kind of wind energy that
Airborne.
is exploiting airborne. So
Uh-huh.
it's exploiting like high altitude winds, and you
Okay.
can use either some kites, so like flexible structures similar to actually the kites that are used, for example, for sport, or other structures, more rigid wing, so called, that are resembling an aircraft, so to say. And
Okay.
they want to actually reach higher altitudes, so to exploit the constant wind and that range. And also, one of the main advantages that they try to underline is that, of course, with respect to a wind turbine, they would require much more less materials, because, of course, a kite is very light and you don't need like thousands tons of steel to have it operating. But of
Yeah.
course, it's still the problem on the other side is that it's not very resistant. So you have to change it a lot of times, almost once a year, they told us.
Wow.
So you need to produce for 30 years 30 kites. And of course, this is also still under development because the rated power are very low. So there are commercial version of this kind of technology that are like 100 kilowatts with respect to the 10, 15 megawatts of the wind turbines. And yeah, the other interesting thing is that they are can be used, for example, off grid. so they could be totally
Mm,
standalone systems. So you just have like one container containing the
mhm.
generator and so on. And so this could be applied, for example, instead of diesel generators for this kind of isolated energy production. The carbon footprint uh, would be quite low, so in the range of 10 grams per kilowatt. But of
Wow.
course, we also have the opportunity to to support some students doing another research on their own, starting from the design to the life cycle assessment of this kind of a kite gen on floating platforms. And this would be instead not convenient as the rated power is too low. And so the energy that you could produce, either if it's made of just like 5 tons of material, the energy is not repaying the investments in terms of environmental issues,
Resources.
environmental
Yeah.
impacts, because yeah, having them offshore with the floating platforms and bringing all the things over there is still too much for the rated power. So although yeah, there's also research on the social acceptance of this kind of renewable energy with in contrast to wind turbines, because there are
Yeah.
people that like wind turbines on the landscape and other people that hate them. And
Yeah.
also living in the nearby, maybe it's disturbing because of the noise and so on. Maybe this kind of energy based on these kites is something not so impactful in the
Mhm.
terms of visual impacts or noise annoyance. So maybe from the point of view of social acceptance is could be better.
Yeah.
That
Yeah. That's a
there
good
are
point.
actually people and researchers on the topic, so something that
That's a
they
good
are
point. That's a
questioning.
very good point. Okay, good. Look, there is one trade union across everything you said, which is the quality of the data, and which obviously it is of the utmost importance if you want to have quality final results. It is a kind of a logic thing. How hard was for you to gather and collect data, especially primary data, as we said before, from manufacturers and from stakeholders involved into the project?
No, actually, it was nearly impossible because, of course, not having the direct connection with the manufacturer or the company who was planning the wind farm, having primary data was just hoping to find them already published or in the literature. So, of course, this is a great limitation to the reliability of the results. But it's the case also when you have the direct contact with the company. It's very difficult to make understand what is actually needed for a life cycle assessment.
When you talk products that are covered by IP, it is always very, very difficult to be able, for obvious reasons. It's obviously very difficult to have primary data. The important thing it is to be transparent, to be upfront, and say this is what we have, this is what we had at disposal to be able to run this number. This is the degree of uncertainty, which is very important to disclose that too, because people then, I'm pretty sure, will take inspiration from your research or from other researches, and say they're 100% sure that those numbers are 100% accurate. Then it is a revolving mistake, a revolving inflated mistake.
Mhm.
They get carried on and on and on and on and on. Look, anyway, Gaia, this was very, very interesting. Thank you for participating into this episode. Thank you for your time. It was great. and look forward to catch up again with you.
Thank you again for having me and giving the opportunity to talk about the research on this interesting topic, but and also giving some space to what is coming to be in the next researches. So it
Nice.
was nice.
Wonderful. Thank you, Gaia. I'll talk to you soon. Thank you for joining us on this episode of Raw Green, brought to you by Obi, a sustainability consultancy firm specialized in life cycle assessment and decarbonization strategies. If you're looking to make an impact, a tangible and measurable one, reach out to us on our website at oneob.com or visit our social media. Links below in the description. See you at the next episode. Ciao.